Here's an example of a Boyle's Law problem. A snorkeler takes a syringe filled with 16 milliliters of air from the surface where the pressure is 1 atmosphere to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If the pressure increases by 1 atmosphere for every additional 10 meters of depth, how deep is the snorkeler? So there's two questions being asked, but let's not worry about those yet. We read through the words, now we're going to pull the numbers out. This is a gas law problem, and a lot of gas law problems have conditions that are changing. There was this circumstance, and then something happened, and then there's this new thing, find this parameter under the new conditions. And so a good way to organize that is by making a table. So I'm going to make a table over here. And I'm going to have condition 1 and condition 2. The first one I come to, I call that condition 1. It doesn't really matter. It's not necessarily an initial and final. So I go through this problem, and the first number I come to is 16 milliliters. So I'm going to write that down here. 16 milliliters. This doesn't say what that's measuring. It's 16 milliliters of air. I know from my knowledge of units that milliliter is a volume unit. So this is giving me the volume of air. So I'm going to call this column V for volume. So that is 16 milliliters at the surface where the pressure is. These two numbers go together, and so I'm going to call both of them condition 1. 1 atmosphere is another parameter, and the unit tells me it's pressure, and the word pressure tells me this is the pressure. So I've got two columns, volume and pressure. Then the snorkeler takes this to an unknown depth. The volume at this depth, that's the second condition, is 7.5. So 7.5 milliliters here. Always include the unit. The unit is part of the measurement. Then the question, what is the pressure at this depth? Well, I look at my table and I have one blank left, one square that's empty. Because that's in column P, I'm going to call that P, and it's in row 2, so I'm going to call that P2. And the question's asking me, what's the pressure? Well, here's my table, and I'm missing the pressure. Then I look at this, and I see, I've got volume and pressure, because right now, Boyle's Law is the first one we're learning. That's the only law we know. Later, we'll have several laws, and then you have to choose the right one. I have volume and pressure, and they're changing. And so I'm going to use P1V1 equals P2V2. That's Boyle's Law. You need to memorize that. I'm going to take the equation, I'm going to rearrange it and solve it for this variable. Sometimes students want to put the numbers in and then rearrange it. I went along with that one semester. It ended badly. Don't do it. It's much easier to rearrange when you've just got letters instead of all those digits and units. So I want P2 by itself. Quick algebra lesson. If I divide by V2, volume 2 over volume 2 is equal to 1. We say those cancel out. If I divide one side of the equation by volume 2, I need to do the same thing to the other side so that it's still equal. Okay? Now, that's sort of messy, so I'm going to rewrite it. P2 is equal to P1 V1 over V2. Be careful when you copy those subscripts, especially it's easy to mix them up. I have an equation. I have all of my variables labeled. I just need to plug the numbers in. So pressure 1 is 1 atmosphere. Write the units in the equation. Volume 1 is 16 milliliters. And that's going to be divided by volume 2, which is 7.5 milliliters. Before you get your calculator out, check the units. Milliliters cancel milliliters. I'm left with atmospheres, a unit of pressure. That's a good sign. So P2 equals 1 times 16 divided by 7.5. Oops. How many significant figures would that have? 2. So 2.1 atmospheres is the pressure. Does it make sense? He's at the surface. He goes below the surface. We expect the pressure to increase, and it does. That's the answer to question number 1. The answer to question 2 is a little bit trickier, and this is where you have to think a little bit. So the pressure increases by 1 atmosphere for every additional 10 meters. I'm going to pull this up to the top. 1 atmosphere per 10 meters of depth. What was the pressure at the surface? It was 1, right? The pressure was 1, and now it's 2.1. How much did it increase? The increase in the pressure, it's at 2.1 atmospheres now. It started out at 1.0 atmospheres. So the increase is 1.1 atmospheres. How many meters does that correspond to? 11. So we take that one, suddenly drawing red arrows. Sorry. Push the wrong button. We can take that 1.1 atmospheres of increase, and we can use this as a conversion factor. For every 10 meters you go down, you get an additional 1 atmosphere. And so that tells us that the diver is at 11 meters. Solving for P2 down here, this is a Chem 3A level problem. And you need to study this stuff until you can just do that almost in your sleep. This part is a little bit more of a 1A problem, where it's making you think about something. Any questions? Charles' law. J.A.C. Charles. So we're moving closer to our own time, but still a long, long time ago. 1746 to 1823. Not going to quiz you on those dates, just for information. He looked at the relationship between gas volume and the temperature of the gas. And he found that the volume of a gas was directly proportional to its absolute temperature. So Charles' law can be stated this way. The volume of a gas is proportional to its temperature, provided that you keep the pressure and the amount of gas constant. So we can write it this way, or this is the most common way. V1 over T1 equals V2 over T2. So there's another equation to memorize. Very important. Now, down at the bottom, this is super, super important. When we're doing problems with gases and we're using gas law equations, the temperature has to be in kelvins. You can't use Celsius or Fahrenheit or anything else. It has to be in Kelvin. Let's look at why that is. Here's an example of a Charles' law plot. So we're measuring the volume of a gas as we change its temperature. So the temperature here is only going down to 0. So they've measured the volume at 0 degrees Celsius, and then they've increased the temperature and measured as the volume increases. And we see that we get a nice straight line. So this is 1 atmosphere. These are all 1 atmosphere pressure. This is the volume if you have 1 mole of gas, half a mole of gas, or 1/4 mole of gas. Well, if we extrapolate, meaning draw a line through the points and go past where the actual data is, we find that all of these lines intersect here at a temperature of minus 273.15 degrees Celsius. That suggests that this is the absolute lowest temperature that's possible. At this temperature, if these lines are true, these gases are going to have zero volume. Is it possible for a gas sample to be compressed so far that it has zero volume? Not completely zero. Atoms are really, really small, but they do have a finite volume. So this absolute zero is kind of a mysterious place. But that's where this 273.15 came from. Negative 273.15 degrees Celsius is equal to 0 Kelvin. It looks kind of like okay, but it's 0 Kelvin. We call that absolute zero. Can't go past that. Zero volume is highly questionable. Negative volume is impossible. So that is the lowest temperature. Yes?
Is this graph with these numbers identical for all gases, or is this like for one specific gas? Like not this relationship, but these specific numbers?
These specific numbers would be pretty close to the same.
For all gases?
Yep. Let's think about what's happening when we cool down a gas. Here's an illustration of a balloon in boiling water and in ice water, and this is something you can do at home. So if we take a balloon that's cold, we put it in ice water to make it cold. The particles in here have low kinetic energy. Kinetic energy is related to temperature. Temperature is a measure of the average kinetic energy of a substance. Low kinetic energy, these particles are moving slowly. This is kindergartners just plodding through the classroom. They're not going to run into each other very hard or very often. We take that balloon and we put it in boiling water and heat it up. Now those same molecules have a lot more kinetic energy. They're going to be moving faster. Kinetic energy is 1/2 the mass times the velocity squared. The mass isn't changing. The only thing that's changing is the velocity. When they move faster, they're going to take up more space. So the volume increases at higher temperature. Any questions? When those gas particles are moving faster, the collisions with the walls are more frequent and they are harder. When you're running at a wall and run into it, that hurts a lot more than if you just walk into a wall, right? In order for the pressure to remain constant, which is what we're doing in these experiments, you have to let the volume of the gas get larger. The balloon is going to get larger. In that larger area, then the collisions become less frequent. They're spread out over a larger area, and so we can keep the pressure the same. I remember as a kid being fascinated by hot air balloons. I mean, I understood helium balloons, right? You put helium in there and they float. I didn't really know why, but they float and it's really cool. But how does this hot air balloon work? There's a giant hole in the bottom of it. Doesn't all that gas come out? No, it doesn't. Because you've got this ginormous burner here that's heating the gas. Charles' law tells us that when the temperature goes up, the volume goes up. If you have the same number of particles of gas and you spread them out, what does that do to the density of the gas? It decreases it. It's the same mass, but the volume has gotten larger, the density goes down. Lighter gases float. Heavier gases sink in air. That's why helium balloons float. And a balloon that you blow up with carbon dioxide mixed with air from your mouth, not going to float. They do in the cartoons, but cartoons like to destroy physics. Pardon me? The idea is that at absolute zero, the particles would not move at all. No one has attained a temperature of 0 Kelvin. I think they've gotten to like 0.4, gotten really close, but nobody's gotten to 0, at least that I've heard of. So the hot air balloon heats the air rises. There's no giant hole at the top of the balloon. I think they may have some sort of a rope or something where they can allow air to come out. I'm not sure about that. But the air rises, it fills up the balloon, and then it causes the balloon to lift off. Here's a balloon it looks like it's in liquid nitrogen. There's my pointer. There it is. You take a large balloon, you put it in liquid nitrogen, it's going to shrivel down because as the gas gets cold, its volume decreases because the particles slow down. Yes. Yeah, we do a science show in the fall, and we do some fun stuff with liquid nitrogen. Let's do a problem with Charles' law. A gas in a cylinder with a movable piston has an initial volume of 88.2 milliliters. If we heat the gas from 35 degrees Celsius to 155 degrees Celsius, what is its final volume in milliliters? So let's make a table and pull these numbers out and organize them. Let's choose the writing tool first. So I'm going to have condition 1 and condition 2. First thing I come to is 88.2 milliliters. So we'll write that down. 88.2 milliliters. In terms of the letters that we use to describe gases, what is that? That's the temperature?
No, that's
Volume. No, the 88. So that's a volume. Has an initial volume. And then it says we're going to heat the gas from 35 to 155. Which of those temperatures goes with the 88.2? The first one, 35 degrees Celsius. Can we use degrees Celsius in gas law calculations? No, we can't. Before you forget about that, convert it right here. Plus 273.15. Of course, it makes my table really long, but 308.15 Kelvin. And what should I label that column? Temperature. This is going to be T. So it's going from 35 to 155. So the new temperature is 155 degrees Celsius. We need to convert that to Kelvin also. 155 plus 273.15, 428.15. We have one empty square, and the question is, what is the final volume? This is the volume of the second condition. Cool. It's going to work out. So I'm going to call this V2. Now we have two equations to choose from. We have Boyle's law with the pressure and the volume, and we have Charles' law with the volume and the temperature. Now obviously we're going to use Charles' law because the title here says Charles' law, but so Charles' law, volume 1, V1 over T1 equals V2 over T2. This equation has fractions in it. Some students have trouble with fractions. There's a great t-shirt. 4 out of 3 people have trouble with fractions. So if you can rearrange this just by looking at it, fine. I'm not talking to you right this minute. For the rest of you, get rid of the fractions before you rearrange it. And we're going to do that by cross-multiplying. So cross-multiplying, you take the top of one side times the bottom of the other. So V1 times T2. That will equal the bottom of the first side times the top of the other side, T1 and V2. And if you write V before T or T before V, it doesn't matter. Just get your 1s and 2s straight. Got rid of the fractions. Now it's easier to rearrange without getting things upside down. I want V2. So I'm going to divide by T1 on both sides. So the T1s cancel out. So I've rearranged my equation. So this scribbling over here, you may or may not need to do. I would like everyone to make the table. And I'd like everyone to do this. Write down the rearranged equation. V2 equals V1 T2 over T1. If you get the answer wrong, we can go back and look at it and see what your problem was. Did you rearrange the equation wrong? Did you put the numbers into the correct equation incorrectly? Did you forget to convert your temperatures? If you write stuff out, I can help you learn from mistakes. So there's our equation, and I'm going to plug the numbers in, being careful to get the correct numbers. V1 is 88.2 milliliters. Temperature 2 is 428.15 Kelvin. And temperature 1 is 308.15 Kelvin. Those units of Kelvin cancel out. The unit on this answer is going to be milliliters. That's what the question asks for. 88.2 times 428.15 divided by 308.15 equals, how many significant figures should I give? 3. So 123, and the unit is milliliters. Then ask yourself, does that make sense? So we're heating the gas. When we heat a gas, does it get larger or smaller? It gets larger. So we expect the volume to go up. It started at 88, it went to 123. We have a change in the correct direction. That's always a good sign. Any questions? Avogadro's law relates volume and moles. Amadeo Avogadro, 1776 to 1856. He was the first one to formally state the relationship between volume and amount of gas in moles. And I believe it was this work with gases that led to what is known as Avogadro's number and the unit mole. So the volume of a gas is proportional to the number of gas molecules. This is very different than for liquids and solids. It doesn't matter how big those individual gas particles are, whether it's helium or xenon. It's the number of particles that matter, not their size. So Avogadro's law says that the volume is proportional to the amount of gas in moles. We measure it in moles because moles is a counting number. It's not proportional to the mass. And this is at constant T and pressure, constant temperature and pressure. So the way we can express that is V1 over N1 is equal to V2 over N2. So same format as Charles' law, but with moles instead of temperature. Equal volumes of gases contain equal numbers of molecules. What the gas is doesn't matter. So here's a graph of data showing Avogadro's law. The volume of the gas in liters increases as the number of moles of gas increase. And it doesn't matter what the gas is. If we extrapolate this to 0, so this was our last data point, if we draw the line all the way to 0, we end up with a prediction of 0 volume for 0 moles of gas. Is that reasonable? Yeah, completely reasonable. If there's no gas in there, not even one molecule, it should have a volume of 0. Lines like this, we have a straight line and the intercept is 0. These are very nice because we don't have, the equation for the line is y equals mx. There's no plus b. So, Avogadro's law problem. A chemical reaction occurring in a cylinder equipped with a movable piston produces 0.621 moles of a gaseous product. If the cylinder contained 0.120 moles of gas before the reaction and had an initial volume of 2.18 liters, what was its volume after the reaction? And in parentheses, we've got the small print. Assume constant pressure and temperature and that the initial amount of gas completely reacts. I think it was kind of mean of the author to put this in as the first Avogadro's law problem. But then again, this law is so similar to Charles' law that if you can do Charles' law, you can do Avogadro's law. So we're throwing a twist in here to make it interesting. Well, let's identify numbers, make a table, see what we have. 1 and 2. The first number we come to is the chemical reaction produces 0.621 moles of gaseous product. So what letter should I title this column? N. Lowercase n stands for moles of gas. So then I come to another moles. If the cylinder contained 0.12 moles of gas before the reaction, well, I already wrote 0.621 in the first row. This has to go in the second row. The fact that the 0.12 came before the 0.621 doesn't matter. I just need to get the amount of gas and the volume paired up correctly. So it had 0.120 moles of gas before the reaction, and the initial volume was 2.18. So this 2.18 liters, does that go with 0.12 or 0.62? It goes with the 0.12. This was at the beginning. Oops. 2.18 liters. And that's going to be volume. Now, we've got a chemical reaction going on, and so this could get kind of complicated. This is saying that the initial amount of gas completely reacts. Because there was gas in there to start with, and then gas was produced. But this down here is telling us all of the initial gas disappeared. It reacted and formed this other gas. And so there's no adding or subtracting that we have to do. Sometimes in Avogadro's law problems, they'll say, well, so much gas was added to the balloon, and now what's the new volume? Then you have to add moles of gas. But this one doesn't do that. So then this is going to be V1. Any questions yet? Getting to this point is really the hardest part for many students. It's deciphering the words and getting the numbers in the right place. Once you get this, it should be fairly straightforward. You pick the equation that has N and V in it, you rearrange it for this V1 that we're missing, you put the numbers in, you do the math. So Avogadro's law, V1 over N1 equals V2 over N2. If you are fractionally challenged, then we should rearrange, we should cross multiply. So that's going to be V1 N2 is equal to N1 V2. And then I'm going to divide by N2. so I can get my equation. V1 is equal to N1 V2 over N2. Any questions? Plugging the numbers in. N1 is 0.621 moles. Always include the units. Next we want V2. That's 2.18 liters. And we're going to divide this by N2, which is 0.120 moles. We check out the units, and the units cancel. Sometimes they'll do tricky things and give you, milliliters for one volume and liters for another, and then you need to do some unit conversions. 0.621 times 2.18 divided by 0.12. How many sig figs? 3. You should always consider significant figures. 11.3, and the unit is liters. That's the volume. Is it reasonable? So here we had less gas, fewer moles, and we had a volume of 2. Here the number of particles has gone up significantly, so we expect volume 1 to be larger, and it is. A common error would be to get your mole ratio here upside down, and then it'll get smaller instead of larger. Yeah.
I'm kind of I'm confused with visually what's going on. I mean the numbers and stuff. So we got 0.212 moles of a gas, and it reacts with something, and that's in a cylinder. Where does something come from?
Well, let's draw a picture.
Yeah. Okay.
Because sometimes I'm a very visual person, and I need to see things. I have learned that I can make pictures in my mind to see instead of actually having to see the thing. But sometimes you need to draw the picture, and they end up being ugly. But hey, if you get the right answer, who cares? I'm not judging you on your artwork. So let's think about this. So here we've got this container, right? And we've got 0.120 moles of gas in there, and it's 2.18 liters in volume. So there's a reaction. So maybe there's a little tiny lump of something, or actually what's even more likely is perhaps this is a decomposition reaction where the gas comes apart and makes more particles. So somehow, that's not what I meant to do. The gas in here is reacting. This 0.12 moles is disappearing. Let's maybe call that moles of A, just some generic gas. And so we've got A reacting to form maybe B and C. It's coming apart to form 2 new gases. This could happen like with water. If water decomposes, 2 waters would give you 2 hydrogen molecules and 1 oxygen molecule. Okay? So all of this is disappearing, but it's forming a total of 0.621 moles of gases B and C. And so the volume has to go up because there's more particles now. Does that help?
Yeah, that helps a lot.
Yeah. If you can't make sense of what the question is describing, then it's really hard to do problems like this. And, reading comprehension is really, really important. Any other questions? If you need help with word problems, please ask me. Because I've heard lots of questions that people would think are dumb questions. But if it's something you don't understand, it's not a dumb question. And you're not going to get anywhere if you don't get the answer to your questions, right? And that's what's dumb. Another example. A scale model of a blimp rises when it is filled with helium to a volume of 55.0 cubic decimeters. That's a unit we don't see very often. When 1.10 moles of helium is added to the blimp, the volume is 26.2 cubic decimeters. How many more grams of helium must be added to make it rise? Assume constant temperature and pressure. Okay, this is taking it to another level. So let's have a picture. Yeah, that's not. Try again. So here's our blimp, right? That's pretty ugly. So I'm going to put 1.10 moles of helium in there, and that's going to give it a volume of 26.2 cubic decimeters. What has to happen in order for it to rise? The volume has to get to 55. So you put some helium in a balloon, and it starts to inflate. How do you get the volume of the balloon bigger? You add more gas, right? So this is what we have to start with, and we need it to get larger. We need it to be 55.0 cubic decimeters. Now, Avogadro's law is not going to give us directly the mass of helium that we need to add. But here we have moles and a volume, and here we have volume. Could we use Avogadro's number to figure out the final number of moles that we need inside the blimp? Yeah, we could do that. So what we're looking for here is N2. So if we make our table, 1 and 2, and say the first set of conditions is 1.10 moles of helium, that's N, and the volume is 26.2 cubic decimeters, that's volume. We want the volume to be 55 cubic decimeters, and Avogadro's law will help us to figure out how many moles of helium are in there. If we know the moles of helium that we need to have in the blimp, and we know how much we started with, we could figure out by subtracting how many moles we need to add. It wants grams. We can convert moles to grams. Okay, so N2. Well, our equation is V1 over N1 equals V2 over N2. Again, get rid of the fractions. V1 N2 equals N1 V2. And you might say, well, why don't they just give it to us like that? I don't know. If you want to memorize it like this, you go right ahead. That's absolutely fine. I'm sticking with this because that's what the book does. But if you want to memorize it without the fractions, that's fine. So I want N2 by itself. So I'm going to divide both sides by V1 because I want to move the V to the other side. So N2 is equal to N1, that's not a V, V2 over V1. So N1 is 1.10 moles. Volume 2 is 55 cubic decimeters. And the first volume was 26.2 cubic decimeters. Look at the units. Cubic decimeters cancel out. We weren't really happy about those anyway, but there they were. 1.1 times 55 divided by 26.2. This is not my final answer, so I'm going to keep track of sig figs, but I'm not going to really round it off just yet. But I should have 3 significant figures here, so that's 2.3 There's the third significant figure. I'm going to carry 2 extra digits. That's how many moles I need. Any questions? The moles to make it 55 cubic decimeters should be larger than the 1.1, right? Because you have to add gas to make the blimp larger. So the question is asking, how many grams do we need to add to this situation to get it here? Well, how many moles were added? We're just going to subtract, right? So we'll take 2.3092 moles. We're going to subtract the 1.10 moles that were already in there. And so that's going to give us 1.2092 moles. And that's going to have uncertainty right there. How many grams is that? Use the molar mass. So the molar mass of helium is 4.003. So 4.003 grams of helium for every mole of helium. The units cancel out. So I've got 1.2092 times 4.003 equals. This is my final answer, so I am going to round. We should have 3 sig figs here. So we need 4.84 grams of helium. Any questions? You should be able to do a problem like this on an exam. It won't be exactly this problem. It'll be something that you haven't seen before.